Hello. Hello, everyone. Good evening. Welcome to uh, episode number 7 of the series of Tuesday Night Live with me, Prince Phaze101, and Emanuela Bonin. Hello,
Hi
Emanuela.
guys, we are here tonight to speaking about Commodore 64 scrolling routines, hardware routines.
So, let's talk the usual things. So, all I ask is that you like my YouTube page and you like the videos. Um, Nothing else from my side in a way. Um, for those that do not know, under each video there's a link, there's a show more, and you get more options to first of all see the chapters, okay, and also to links to code, etc. So the code for this episode there will be a link under the video for it. Besides my YouTube, of course, please like the Retro Programmers Inside YouTube channel. And funny enough, I see myself. And also the Retro Programmers Inside Facebook group. Please join the group if you want to enjoy doing our game jams, if you would like to do our game jams and you enjoy doing that. So, same as Retro Programmers Inside, I have my Phaze101 page. Please follow the page, subscribe, and join the Phaze101 Facebook group. There is a hidden message for those that do not know in the where there is 101, the binaries. If you manage to decode them, there's a message there. For those that never realized. And then there is the Commodore Dev Facebook group. Please subscribe and like things there.
Yes.
If you would like to chat with me, there is not just Facebook, which I look at it, but not so often. There is also Discord. You can join on Discord and hello, Chunkies. Thanks for the follow. You can join Discord and you can chat with me directly there.
Chutney is 5. Hi.
I have also
Yes.
I also have a Telegram group. If you want to join to my Telegram group. If you like what I do, you can also support us by coming on Patreon. If you join, you unlock 68 videos. Same thing on Coffee. So that's basically it, and we can jump to visual code. So today we will be doing and teaching you in a way, or showing you how to do scrolling, vertical scrolling on the Commodore 64. I will show you what Emanuele did, but there you go. this is what we will be doing. You will learn how to scroll a screen on the Commodore 64. So, without any more delays, okay, I will live share to Emanuele. Okay, Emanuele, you can start.
A moment, please. Okay. 0501.
Yes, 0501. Yes.
Okay. In this little example, I try to explain how hardware scroll works on Commodore 64. In the Commodore 64, we can scroll smoothly the entire screen without moving memory blocks in any direction. But we can scroll it for a maximum of 7 pixels. Even if it sounds like a limit, this limited scroll is enough to move smoothly the entire screen and desired number of pixels. The trick is to move smoothly the screen on every frame by 1 pixel until we reach the 7th pixel. After that, we start again from a position 0 pixel. But if we move the entire screen memory of one char into the scrolling direction before the next frame, we can create the smooth scroll illusion that is limited by the hardware scroll. For example, I try to write an example with a little table. In the first column of this little table, we have the frame counter. In the second column, we have the hardware scroll position in pixel. And the third column, we have the amount of the entire screen scrolled from the beginning. The moment we move all characters of a screen one line up. If we follow the table, we can see that for the first 7 frame, when the frame change for the first 7 times, the hardware scroll changes synchronously 1 pixel forward. And we don't move the memory blocks from the screen. We don't make a char scroll in this first 7 frame. After the 7th frame, the hardware scroll is resetted to 0, and all and the whole screen is moved one line up in this example. In fact, in the third column, we have for 7 times the number 1, indicating that one line up is moved, and so on.
So, if this is our screen, okay, and we have our rows of characters on the screen, this is the first rows, so line 0, line 1, and this is line 25 at the bottom. So, I was saying, when we scroll the screen, okay, we have a hardware scroll which is only from 0 to 7, and that shifts the screen up. However, once the screen is shifted up by 8 pixels, it returns back to where it was. Therefore, we need to copy what is in line 1 to line 0, and we continue like this. What we have in line in line 2 goes into line 1, and continue till we arrive till line 24, sorry, 25. What is in 25 goes into line 24. At the bottom, okay, as Emmanuel is going to say, what he's doing is copying the top in this case, okay, only in this case. Normally you don't do that. But in this case, we are doing a roll. So what's on top goes into the bottom. That's how the hardware scroll works. There is more to it, but for now, let's be like that. Let's not go into more detail.
Okay.
Please notice that Emanuele said this. If we do 7 to 0, we shift the screen up. If we do from 0 to 7, so the shifting of the screen, basically, we do the screen shifts down, okay? This is important in a way to know. You just need to know. Notice also that in this table, okay, we are shifting the screen, okay, till we arrive 7, okay? We haven't scrolled the line, we haven't copied the lines, so from line 1 to line 0, but once we reach 7 and we reset to 0, we do that, okay? We do the copy. And we continue again doing the shift, okay, till we hit 0, and then we copy again. This is the second time that we have copied from line 1 to line 0, and all the other lines, of course. And we continue like that. So,
first of all, thank you, Amok64, for your words. How the Commodore 64 can make this hardware scroll? It uses two hardware scrolls register in present in VIC2. One for vertical scroll and one for the horizontal scroll. Each hardware scroll registers uses 3 bits, which gives us a range from 0 to 7. In this program, we will scroll smoothly the entire screen up with the rolling effect. So the first line or top line of the screen will be copied in the last line or bottom line of the screen when the entire scroll will be triggered. We will use a raster ERQ that is interrupt. ERQ is a short mode for interrupt, but most of you said yet. That is triggered, and at the beginning of the lower border, when our interrupt service routine will be called, we will scroll pixel 1 up. So in this case, we have a count from 7 to 0 to make the illusion of scrolling up. When we reach the 0 in a frame, we have to scroll the entire screen up by one line at the next frame. This operation is cycle consuming, so it is important that it will be optimized to avoid the glitches on the screen due to synchronization from the CPU and the VIC. Until now, it was illustrated how to move chart smoothly, but no character colors. If we want also color, we have to scroll these to when the scroll chart event occurs. But in this case, in this example, we will not have moved the character colors. To do this, we need to use other methods, since this will require more than one frame cycle to move the entire screen with color. So there are other techniques. to scroll the entire screen with color will not be covered in this program, obviously. To move colors and charts without problems, we have to scroll only some part of the screen. Using the hardware scrolling, the entire screen will move up by 1 pixel in that direction. This means that the shift will create a null of 1 pixel line each time in the opposite border position of scrolling direction. To hide this, the VIC can reduce the number of rows or columns by expanding the borders and overlap the lines. This is enough to create the scrolling illusion. Expanding the borders, we hide the holes that the hardware scroll will create.
Oh, okay. Let me go through that quickly.
Okay.
Guys, I do this also to give him a rest, okay? To give Emanuele a rest, because it's difficult when it's not your first language. So, as Emanuele said, there are two hardware scroll registers, one for the vertical scroll and one for the horizontal scroll. And each register uses 3 bits from 0 to 7. So that gives us 3 bits gives us from 0 to 7. In this program, we'll scroll smoothly the entire screen up with a rolling effect. By rolling effect, I have already explained it in my diagram that what's on top goes at the bottom. That's what he means by rolling effect. The top line goes at the bottom line. The first line or top line of the screen will be copied in the last line. He wrote it here. When the car scroll will be triggered. Yeah. We will use a raster interrupt that is triggered at the beginning of the lower border. So that's something I need to show. So our interrupt routine, okay, will be triggered somewhere down here. To be fair, because this line is hidden, okay, we can trigger it even earlier. So we will trigger it somewhere here, okay? So if normally you trigger the raster interrupt at line 250, let's say, today we will do 246, I think, or something like that. I can't remember.
Yes, to gain some lines.
Yeah, so like that you can gain some scan lines. The reason why we need as much scan lines as possible is because the Commodore 64 to scroll a screen takes time. The CPU, this is CPU intensive, to scroll a screen. Hence why you're trying to gain as much as possible. And as Emanuele said later on in the text, it is even more consuming if we use color, but in this example we are not going to use color. When the interrupt will be triggered, we will scroll by 1 pixel up, okay, till we have done all the pixels. Then we do the scroll. Till now, and even in this example, we will only scroll the characters without the color. Yeah, he's saying in this example, we will not move the character colors. To do this, we need to use more other methods. It's a different technique. And there are different techniques to scroll the screen with color. Using hardware scrolling, the entire screen will move up by 1 pixel in that direction. That means that the shift will create a hole. He's calling it a hole. But imagine what will happen if you scroll, let's get the diagram. It's okay.
You can.
So if you scroll the screen and you copy line 25 to line 24, okay, this is blank. But also, what happens is when the screen is being shifted, okay, automatically here, down here, okay, there will be blank while the screen is shifting. And we can show you this later on. But right now, just a method of saying, imagine like garbage coming out. That's the right way. And the Commodore 64 has a way of hiding that garbage. So the VIC chip has a way of hiding this, as I said, and it does this by reducing the borders, collapsing the borders, basically. Sorry?
Expanding the border.
Yeah, you can, it depends how you look at it, but yes.
Reducing the background and expanding the border, I
mean, the
mean.
borders become bigger. Yeah. This is enough to create the scroll illusion. Okay, so now, Emmanuel, you can continue. You still have control. I didn't take control, so you can start highlighting.
Okay. Now I try to examine the two VIC registers that we can use to make hardware scroll. The first register is the control register 1, that is DO11 X, is useful to perform a smooth scroll vertical hardware scroll. Okay. This register is an 8-bit register, like as usual in the Commodore 64. The bit 7 is the raster 8-bit. We have used it in the past, this bit. This bit is useful to track the raster line within DO12X, when raster beam supersedes the line 2055. This bit is set to 1 if raster beam is beyond the line 2055. Follows follows the HEM bit, the bit number 6, extender color mode. This bit is used to extended color mode. To use the extender color mode, the bit 5 is the bitmap mode. This bit is used to set the iris mode, 2000 pixel for 320 pixel. HEM, ECM, and BMM are used with the bit MCM. Is scioglilingua, non so come si dica in inglese.
Yeah, just say extended color mode, no, and bitmap mode for them. That's all you have to say.
Okay. On DO16X register to select a particular screen mode. So with these 3 bits, we are 8 combination, but not all these combinations are valid. Anyway, these bits, I do not use these bits in this example. The bit number 4 is called DEN, display enable. It is used to switch on and off the text or the bitmap graphics screen. Normally, it is used to affect two functions of the VIC. One is the bad lines that we have covered in other lives and preceding lives. And 2, the vertical border. Anyway, this bit 2 is not covered by this example. Now, there is one of the bit that we use, the bit number 3, that is called R cell. If this bit is set, the upper and the lower border are expanded. So the visible number of line becomes 24 instead of the normal 25 rows in the screen. This bit is used in this example to hide the part of a screen that will remain empty during the smooth vertical scroll. We can try to not set it during the example to see the ugly effect if we don't reduce the number of lines. The 3 bits, the 2 bit 1 and 0 bit 0, 1, 2 contains the value that indicates to the VIC how many pixels the graphics text will be shifted normally. These 3 bits have a value of 3, 0, 1, 1. Okay. On the other part, there is the register number 2, the control register number 2, that is DO16 hexadecimal. This register is not used in this example, but is useful to see its bit. In fact, with the DO16, can perform the horizontal hardware scroll.
Yeah,
okay.
I'm going to stop you. We are not using this register because we are doing a vertical scroll, not a horizontal scroll.
Okay.
That's why we are not using it.
In this register, only 5 bit, only 6 bit are used. In fact, the bit 7 and 6 are not used. The bit 5, this bit is isn't used by the VIC of the Commodore 64, but is used by the VIC 6566 VIC2 chip found on the C128. This bit is used to stop the VIC2 and be able to use the 80-column screen of the Commodore 128. From Christian Bauer manual 1996. But this is for me is the Bible of the VIC. All that I know, I read firstly in this manual. Okay, the MCM, the multicolor mode that we have encountered above, is used within ACM and BMM bit on DO11X to see the display mode, see above. Okay, so the MCM is the bit number 4, sorry. The bit number 3 is the C cell, that is the counterpart of R cell in the DO11, sorry. In fact, this bit is, if this bit is set, the right and left border, the vertical borders are expanded. So the background color really, the background columns, sorry, really visible are only 38 normally are 14. This bit is useful to hide the part of screen that will remain empty during an horizontal hardware scroll. The X scroll indicates the bit 0, 1, and 2 of this register. The value of these 3 bits indicates to the VIC how many pixel lines columns. The screen will be shifted to the left or right. Normally, these 3 bits have the value of 0. Are resetting are all 3 0. Okay.
Why did you say columns?
Sorry?
Why did you add the word columns? Perché hai aggiunto la parola columns?
Instead of row lines, because
No.
it's not a typo.
Oh, okay. But okay.
Because if you scroll to the right or to the left, you scroll a column of pixel.
That's
I
what you
mean,
mean. That's what you mean, a column of pixels. Okay.
a column of pixel.
So, shall I go through them quickly? So, like that, I give you a rest.
Thank you.
So, first of all, for Emanuele and for myself, okay, here is the link to the Bible of the VIC2, okay? Or everything is explained there. Anything that, I mean, there are lots of things that are not in the hardware reference manual of the Commodore 64 and how to achieve certain things. So if you read that book, okay, the textbook is the same thing. It's pixel, he means pixel columns, not character columns, which, yeah, it is pixel columns in a way. I was saying that text, which I can show here. Okay, plus. This is what you need if you want to learn more about the VIC2 chip. All these examples that we are showing are based from this, okay? From this text that Zimmer did. So, I'm not going to go through all the bits because they are not really important for us in terms of scroll, of Y scroll, but we have used bit 8, okay, for the extended bit, let's say, that for the raster line, so it's bit 8 of the raster line, ECM and BMM, and then we have seen actually ECM and BMM is not something we have covered. It's extended color mode and bitmap mode. Then we have seen it because you can switch the screen off. We have seen it in the previous examples also. This bit, okay, is important because with this bit we expand the borders, okay, and we make them bigger, the top and bottom borders. And of course, Y scroll is our 3 bits which are used for which are used for scrolling or shifting the screen, because that's the right word. I think it's shift of the screen. D016, which can do horizontal scroll. The first two bits are not used. Res is used in the Commodore 128. It is not used in the Commodore 64. I need to have control. It's not used in the Commodore 64. And it is used, okay, to switch off the VIC2 chip and enable the second chip that the C128 have, which is the 80 column mode. So basically you switch the VIC2 chip and you enable the other one. That's why it is there, that bit. This is used, the MCM is used for multicolor mode within the ECM and BBM, which are enabled here. And then we have again the C select. So basically you enlarge the borders, the left and right, so the screen will not show us anymore 40 characters, but will show us 38. The first column and the last column will be hidden. Then we have 3 bits, which will shift the screen from 0 to 7 in the X direction, in the horizontal direction. Here is the code, and Emanuele can start explaining them. Emanuele, I don't know if you noticed, but I put these comments. This is the sequence that we should explain each routine, just to make you aware. Okay?
Okay. Okay. First of all, as usual, I defined some constant to have for the register of a VIC, the DO12, the raster counter, the DO1A, the VIC ERQ control register, and DO19, the VIC ERQ status register. The screen, this is the screen RAM address startup that Commodore 64 normally uses. The color RAM, no. Okay, this is the color RAM address, but like we said before, we will not use it. Okay, this is the constant. We will that is the raster beam line to start my interrupt service routine. In fact, normally this is 251, but we will working in 20 rows mode, like James said some minutes ago. So the visible part of the background is rinked, and the interrupt will be triggered at line 246 instead of 251, gaining some precious cycles. In this case, 5 line of cycles. Okay, every line is about 64 cycles, 65 cycles, depending on, okay, 64. Now, here we will our program will start. First of all, I call a simple routine that fill the screen In fact, with no fantasy, I called it Phase screen. Okay, Phase screen. This is this is the start, and this is our routine. Fill the screen with some garbage charts without without colors, but I wrote anyway the code because I don't remember why. Okay, so to fill all the screen, we looping through the.
Vuoi che spiego io? Emanuele?
Sì, sì, spiega tu, scusa, perché mi sto perdendo un attimo.
Okay. Okay. Emanuele got lost a bit. So basically, this is his fill routine. As you notice here in the middle, he also can give color to the scroll, to the characters on the screen. But he did it just probably for testing purposes. In this example, we do not need it. That's why it is commented out. Basically, we just initialize the Y register with 249. Okay, we set the do you want to
Pseudo.
sorry
And the LDA command, are you looking
yeah
for the LDA?
yeah you're
Okay,
setting
the
there must have
LDA
been
command
position,
is
no?
only for load a pseudo random value.
Yes, so
No.
you're just setting you're just loading the DO12 with a random value, I mean whatever value it has, okay, and then we are storing that at the screen positions. So screen is 1024, then plus 250, then plus 500. So basically he's filling the screen with random characters on the screen, and these random characters are coming from the value of the VIC. It is needed because it will do one more, but anyway, it's don't go into don't try to look at the hair in the lake, okay? Because whatever. So that's all it does. Because now this is the part that is interesting, and this is what so Emanuele, do you want to explain the initialize IRQ?
The initialization of okay, sorry. The other
you know why there is copy $FF? Because 24920, okay, is to 50, but 0 needs to be done. That's why there is FF. So to do 1000, okay, you need the FF there. I mean maths, no? 0 to 50, 700, 750, 1000, but that's why it is needed. Sorry, Dockster, but it's why. I mean, he's not count. He wanted the 0 to happen. If he started to 50 here, then yes, but then he will need to change something here. So that's another way of doing the loop. Not to defend Emanuele, okay, but
ok, ho dovuto usare la comparazione con dollaro FF. Allora, gli volevo dire, siccome parto il conteggio di Y da oltre il valore di 127,
Sì,
eh, il valore è negativo se usassi la funzione branch for plus, BPL,
sì,
ok?
ok.
Quindi non mi farebbe il ciclo completo.
Sì, ho
Quindi
capito.
ho decrementato, e decrementando ogni volta controllavo FF, perché FF viene subito dopo lo 0 quando
Sì,
decremento di
sì,
1.
sì. So, Dockster, he could not use BPL, okay? Okay, because he needed to follow the he needed the FF to so that zero is done. Emanuele, you can explain the initialize IRQ, I think. Okay, you have control.
Okay. Okay. So after this fill screen, we initialize the interrupt, the ERQ. So to initialize the ERQ, I used the same routine that we used in the other lives, in the preceding lives. But this is the same routine that I will explain anyway. First of all, we should disable interrupt, the maskerable ones. So we disable the various ERQ of CIA1 and CIA2, and clear any queue of the CIA1 and CIA2 with this bunch of opcodes, loading this value and storing the value on these registers, DCOD, DDOD, and DCOD, and after all, DCOD and DDOD in X to disable ERQ. To clear eventually queued ERQ on CIA1 and CIA2, we perform a load of the register DCOD and DDOD. This is enough to clear the queue. So after this, we banking out the kernel and the basic to have all 64 kilobytes of memory at our disposizione, come si dice?
To our
A nostra disposizione.
Yeah, to our disposition.
Loading this value in the accumulator and storing the value in the byte one of the that is the configuration byte, with all capital letters, the configuration byte of Commodore 64. Okay. With these two lines, we are loading the low byte and high byte of our raster routine that is this. Essentially, this is the initial address of our routine that I call my ERQ. With this opcode, I load the low byte of this routine in the accumulator and the high byte of the address of my routine in the X register. After that, I store the accumulator, that is the low byte, and the X in the vector, in the interrupt vector FFFE and FFFF, that is that I can use because I banking out the kernel and the basic. Okay. After that, I set. First of all, with this bunch of codes, I said to the Commodore 64 where the interrupt will be triggered. So after the ERQ handle that is set, now I'm setting the raster line value where the interrupt will be triggered. Loading on the accumulator the value that we saw before, 246, that is on the RST underscore my ERQ, and store it on the DO12 register, that is the raster line counter. Having to activate the raster for one raster line less or equal than 255, I'm going to set bit 7 of DO11 to 0. The bit 7 is the bit that we saw before. That is the bit to be able to count the raster line when they are over the 255. Okay. Using this bunch of opcodes, loading our VIC register DO11 and masking it with this value that resetted bit number 7. So storing it again to DO11. Okay. Now we should setting the screen to 20 rows mode, resetting the bit number 4 on DO11, like we said before. This way we cover the part on the screen which with 25 lines would reveal the trick. Okay, after perhaps we can try to see the trick, to see these effects. Okay. O-ring. Okay. Here we reset the bit number 4 with this operation, ending this value on the VIC DO11 value. After this, we make an OR operation with this value. Okay, setting the Y scroll, the Y scroll to 7, because we are scrolling up. Okay, so we start from bottom. From bottom. The bottom is the value of 7. and after that we store the new value of our register DO11X. Now we should say, we have to say to the Commodore 64 that our interrupt to activate is the interrupt associated with the raster lines. Okay, loading this value, the value 1, on this VIC register, that is the register of the interrupt of the interrupt, to setting the interrupts. After all, we enabling again the interrupts. So after that, the interrupts on line 246 will be triggered and will call our interrupt service routine. So with RTS, we come back here.
Okay. Okay, I will explain the initialization IRQ. I'm going to make it a bit bigger. Oops. Give me a second. Okay, Dockster. I hope it's better. So, this part of the code, we have already explained it in the previous examples, but what we are doing here is we are setting, we are telling the Commodore 64, hey, we want an interrupt, and we are telling the Commodore 64 that we want this routine to be executed every interrupt. Okay. Now, how do we start? Like the previous examples, we disable the interrupts, we disable the CIAs, and then we disable the basic and kernel ROM. Okay, this is standard stuff. You should all know it. By now, we are in episode 7, so if you have any issues, just say. Then we set up our interrupt routine in the vector FFFE and FFFF. We can use these two memory locations because we disabled the kernel and basic. Okay. So now we need to set the raster, where we are going to have which raster line will trigger our interrupt to execute our routine. So this is what will trigger it. Where is the line? VIC RSTDO, this one. RST my ARQ, RST or my ARQ, what value it is. So at line 246, we're telling the Commodore 64, okay, that we want to trigger our interrupt. Okay, here we I always forget these registers by heart unless I look at the manual. Okay, here he's making sure that bit 7 is 0 of, so basically this bit. Okay, because we just want on 246, so this bit is 0, so he's making sure that it is 0. Then he's setting 24 row mode, So basically the border, top and bottom shrunk a bit or expanded a bit. Sorry, expanded a bit to use Emanuele's word. And he does this here. And then he says, okay, now start doing this interrupt, basically. So bit 1 is the interrupt. So that's the routine for setting the interrupt. I mean, this is what really, after we did all our setting, telling it, hey, we want the interrupt to happen on 9246, and we told it which routine we need to execute. This is the line that starts the interrupt, okay? That says, okay, this is, you need to start monitoring this now. All we've done here is set up an interrupt routine, okay? So Emanuele can continue with the next routine, which is, actually I can do it this, just to give him. So we have an infinite loop, okay? So the program will loop forever here, but because we set up the interrupt routine will start executing, and Emanuele can start explaining my IRQ, what it does. Okay? So when the interrupt is activated, every time the raster hits 9246, this routine is going to be executed. Okay? This routine will call another routine, which is this one, but we will explain later. So, Emanuele, can you start explaining my IRQ, please?
Okay. Can I take control?
Oh, yes, sorry.
Okay. Okay. This is the interrupt service routine is called, like James said, when the raster beam hits 246 line, the line number 246. So the first things that we must do is saving the register value to the stack, or in some other ways. In this example, I'm using the stack with these opcodes, saving the A register, the X register, and the Y register. The first thing that we will do is acknowledge the interrupts to avoid that the interrupts continue to trigger even if it's not the right lines. The service routine is sent to the CPU that ERQ is served. Okay. This opcode substantially reset the bit on the register that say to the CPU that ERQ is served. Okay. Now, after that, I decrementing the pixel scroll number that is a byte defined here. Okay. But it will start with a value of 8. Okay. This is the counter of the pixel scrolled by the hardware scrolled routine. Now I decrement the pixel counter. If the PSG, the pixel counter, is 0, okay, with this opcode I'm testing these things, the pixel counter 0. we reached the minimum hardware scroll value. So we have reached the 0 pixel shifting, and we have to scroll the entire line to reset and reset the our pixel scrolling again. Okay. So if we have reached the value of 0, we jump to this address that is here. Okay. So here, first of all, we set the pixel scrolling counter to the maximum value, that is 8. Okay. With assigning 8 to the x and storing x to the pixel. Pixel is our counter. So we have to resetting, even if to setting the D011 Y scroll to 7 with this opcodes. Okay. So after that, I should I have to roll up all the screen, because I'm if I'm here, I reached the top of my hardware scroll. So I will roll up all my screen of 1 lines. Rolling up 1 lines of screen, I will go here. Now, here I initialize the y-index register to 39. This index is used.
Emanuele, you needed to explain only this, not this yet. Okay, so I stop you there and I go again. Okay?
Okay.
So, first of all, I need to answer Amok. Amok, in this case, okay, and only in this case, I'm going to tell you why. So Amok has asked that it will still glitch even though we are starting here at the bottom. It won't, Amok, and I tell you why. So we start here. Of course, somewhere down here is 312 or 318. Okay, and then it starts again from somewhere here at 0. Okay, while it's doing this has already moved. Okay, so it will take time to catch it. It will not manage to catch it. But note that we are only scrolling with no color. If we were doing color, then yes. So that's why we stated that it is without color. So it will not catch up. So once it's doing here, I'm pretty sure you're understanding me, Amos. Once we are doing here, it would have already moved, I don't know, 3 lines or 4 rows. The example, I already ran it. You missed it then, Dockster. I show you. Let me run it again. That's what we are doing. So random characters on the screen and we are scrolling them. Actually, good point. We should make it more available, much for people that join later. For people that join later, we should show this more often. So good point, Dockster there. So because we're starting our raster line, our interrupt somewhere here, while it's doing this part and also the hidden part of the screen and goes up here and continue doing this, it will not catch up. And I'm trying to slow it down, but no, it's okay. It's doing it properly. So let me explain what Emanuele did. So we have our interrupt routine. This is our interrupt routine. So he saves the registers first thing. I was saying he saves the registers, then he checks. Okay, so he acknowledged the interrupt, sorry. He acknowledges the interrupt. Then he checks if we have reached the 7 or 0, 0 in our case. Okay, if we reach 0, okay, then we need to call, where is it? We need to do the roll up. Okay, if not, okay, we continue, okay, with the scroll, which is scrolling 1 pixel, okay, and he jumps here. Here, he just restores the registers and return from the interrupt. But when we scroll 0, when we arrive to 0, then we set our pixel counter back to 8, okay? Because we're doing 0, 8 to 1. When it's 0, we take action, basically. Then we set the scroll register again to 7, okay? And then we do our roll-up routine, which he will explain in a minute. While we are here, where is it? The bit, Emanuele, the bit that we do not expand the borders.
Is at the beginning.
It's here. That is.
I'm setting it at the beginning of the source.
Where are you setting it?
When I setting I'm setting the.
Show me. You have control. Show me where you're setting it. You have control.
Resetting the bit number 4 of. Sorry.
Yeah, scroll.
Can I?
Yeah.
Okay. Here. Here.
Okay. So if we make this
bit number 4, this
yeah,
way
if we make this 0,
if we
make this 0, we do not expand the border, and we can see what happens, no? Right?
Yes. The 4th bit, that is the bit 3.
Yeah, bit 3. They start from 0.
Sorry for my loud voice.
Yeah. No, but they start from 0. Always.
Yes.
Okay, so this, okay, should be 1 or 0. That should be
0.
So, but how come it is? Okay, wait. I'll show you what I mean.
Okay. Place 1 and place 1 and try to run again the example.
Yeah, exactly. That's what I want to show. So if this is a 1, there you go.
Sorry, no. No 1 here. Can I change?
Why? Because this is what's happening. Look. This is what I wanted to show. The
No,
garbage
if
at the
you
bottom and
place
top.
one here, you don't set the bit free. You should place one here
Ah,
on
that's
the
what you mean. Ah,
on the
okay.
or.
Okay. Sorry then.
Don't worry.
Okay, so let's do it again. Okay, okay. So, yeah, but it's still same effect because it was an and then an or. Look, this is what it does. The screen is shifted, but we have this, I don't know
And
how
don't
you
say
call
the
it. What remains, no? It's like it's. Can you slow it down? Yes, we can, no? To see exactly what really happens. Look, you see that there is a space while it's shifting. So when we create the
put,
border, when we expand the border, that is hidden.
yes. Okay.
Yeah,
Yes.
you see it at the bottom and you see it at the top. Okay, so three lines, I think three
Yes.
scan line,
Four and four.
3 or 4, something like that.
Is one line, is one character line in total.
Yeah, but if you take the top and the bottom together. So yeah, the most important thing, no matter how many they are, is that you see the lines, the void at the top and at the bottom. Okay, whether it's 3 raster lines, 4 raster lines, whatever, or 4 pixels, 3 pixels, doesn't matter. So that's why you need to expand the border to hide that, basically, because the screen is being shifted. So once we expand the border, that vanishes. So let's put.
You can see a little glitch in the bottom part of this
Yeah, of
screen.
course, because with the raster line is starting at line 246, so there it will
Yes.
be glitch.
Yes.
So that's why it will glitch there. But because we started with the border expanded, okay, it doesn't show up. That's why. Dockster, yes, but remember, we are not doing the code to be like demo coders going into the minimal, to save a byte there and a byte. Here we're trying to explain the theory behind it. But yes.
Yes, you are right, Doctor. It's true.
It's just for simplicity, we're doing these things. Okay, so now Emanuela needs to explain the roll-up routine. Okay.
Okay, I'm trying.
Hold on, because this is still showing my fixes. So ignore what there is, okay? Ignore. Okay, so you can explain that.
Okay. The roll-up routine essentially is a routine that, first of all, will copy the first line of the screen, the upper line, on the bottom line, and all the line in the middle are shifted of entire line one up. So first of all, I make a loop to save the first line of the screen in a buffer. My buffer is called the raw buffer, that is defined here.
Oh, Amok, oh my God, Amok, thank you.
Okay, so I defined a little row buffer here with this. Okay, the row buffer is a place where I reserved 40 bytes for the roll up operation of the first line. In fact, in the row buffer, I will copy the first line when I must go. I must roll up the entire screen. Essentially, I make a loop of for the all 40 characters on the first screen, and save the first screen to the row buffer using this bunch of opcodes, loading X, using Y like indexed, copying the first line, that is this, to the row buffer, and these two opcodes copy the first line to the buffer, and in the same way I copy the second line to the first line. So I move I save the first line with this, and I move the second line to the first line with these two with these two opcodes. After that, I close the loop with BPL, a branch for plus extraction. Now we have to shift all the other lines. So I initialize the Y register to 0. Okay, here is useless. This is repeated. Okay, and initialize Y to 0 because our goal is to copy the 256 bytes on following free loops. I'm trying to make this in a way, in a quicker way, in the quicker way, to avoid the glitches when change the frame. So essentially, I use free loops, that is one copy of the other, except for the starting place, copying 2056 bytes for every of these free loops. So I will copy 768 bytes, shifting it one row up. After that, I will complete the roll up, reaching the 1024 byte. Is in X these things. Is is an hexadecimal. Okay.
So just to recap, okay, I'm just going to show my diagram again, my famous diagram that I did 5 minutes before this stream. So the roll up, okay, he's copying this line to this line. That's the first part that he does. But what's in this line, he's also saving it so that then he copies it at the bottom line, because all the lines are going to move up. Okay, what he's doing here is he initializing 27 is 39. Okay, so basically he's going to copy the row 1. Okay, so plus 28, which is 40, is row 1 that goes into row 0. Okay, in the meantime, in between, he is saving it. That's all, and it's a loop. Okay, ignore my code. Okay, do you want me to continue to explain this, Emanuele, or you want to explain it?
Continue, please.
Okay, then after he does the first row, he does the next 256 characters. Okay, so basically he copies the rows, so from second row to first row, etc., 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 and it continues like that. Okay, and then he does the next bunch of 256 characters. Okay, and again starting at screen position plus 150, and from this position he copies to this position, which is 128, and now he has done 512 characters on the screen. Then he does the next 768, the next 256, which brings us to 768. Okay, but then he needs to copy only 152, not 256, to reach the 1000. Okay, he called it loop 1024, but he's reaching 1000. Okay, once he's done that, he copies the top line that he saved to the bottom line, basically, and that's basically it. So all routines are explained. I'm surprised how long this took us to explain it, actually, because we have another one, but it's already 2 hours. So
we can show the
yeah. The other thing
result.
is that yesterday I was talking. Thanks, Duncan, for the cheers. Thank you very much. So yesterday I was explaining to Emanuele, okay, just how to shorten this. Basically, it's not important, okay. It's not important. It's just a way of doing it. The first row, how we can shorten it, but that is all. Basically, I can eliminate this code, this line, and with this code, and these 6 lines becomes 4. 2, 4, 6. Yeah, these 6 lines become 4 by my method, but it doesn't matter. The rest is the same. I didn't change. I mean, I have other ideas how to improve this, but it doesn't matter. The important thing is that you understand the concept. Optimization is not something that we go here. Most of the time, if you have to use optimization, the code becomes complex and difficult to explain to newcomers. So this is why we use these things. Basically, we are what I do with the Amiga on Saturday and Sunday. We are using the same principles to keep it simple. Okay, the KISS method, keep it simple, stupid, so that for those that do not know what KISS means, so that we can understand, beginners can understand. Okay, Andres, see you on your stream probably. Okay, so I'm going to show you the example that we will do next week. Now, this example, there are others that will follow, okay?
Sorry.
We thought we will only manage to do this one, but actually we never started it. So this is what it does. Now, it's just a scroll, okay? Horizontal scroll of the same sentence at the top of the screen, but looping. What you don't know is there's something that maybe some of you that knows how to do scrolling, okay, we do it completely different. Emanuele uses a nice static of how he does it. I'm pretty sure most of you has done something like this, but not, and I haven't seen even Shalan using this technique. So yeah, we will explain it next week. So guys, thank you very much. I hope to see you Friday or Saturday, Sunday. Friday, I'm not sure I'm going to stream, but if not, definitely Saturday, Sunday. Okay? Thanks, Amok. Thanks, Doxter, and thanks all that followed. Thank you, Emanuele.
Thank you all.
Yeah,
guys. Thank you, James.
And hope to see you in the next stream. Thank you. Bye-bye.
Thank you all. Bye.